You open an app, tap a button, and a movie instantly streams to your screen. The experience is effortless. But hidden beneath that polished surface is an ocean of raw complexity, where isolated pieces of code fire simultaneously, in the dark, to process logic, retrieve data, and authenticate users. Left to themselves, these isolated scripts have no structure. If they run blind, their paths cross, errors cascade, and the entire platform shatters under its own weight. To survive, they need a master plan. Software architecture is the strict structural grid that organizes these fragments, keeping massive digital platforms from collapsing into entropy. The most basic worker within this structural grid is a component. Every component must export a specific capability, like processing a payment, and import required services. If a component changes its response format without warning, the connection fails, paralyzing the workflow. Connectors, like REST APIs, act as rigid contracts, verifying compatibility before data flows. Modern engineering teams spend immense effort managing these interfaces. Enforcing safe, predictable connections transforms isolated files into an unbreakable chain. Zooming out to the macro level, managing millions of these connections requires heavy organization. Engineers don't guess how to assemble them. They rely on proven architectural patterns to quarantine errors. In enterprise systems, this takes the form of layered architecture. The environment is separated into vertical tiers: user interface, business logic, and persistent database. Information travels systematically through these pathways. A web frontend talks to the API, which calls business services, accessing the database. By forcing data, visuals, and user interactions into separate compartments, championed by the model view controller pattern, updating a visual button doesn't risk corrupting the underlying server records. Because functions are physically quarantined, individual engineering teams can update and scale their specific part of the application entirely independently. Separating concerns establishes clear boundaries. It gives enterprise software the clarity and maintainability required to handle massive global traffic safely. While layered architectures provide heavy-duty order, modern cloud platforms also have to react instantly to millions of simultaneous users. That requires a much more fluid structural approach. This is the domain of event-based models. When a user clicks buy, that action acts as a digital heartbeat, sending an event across the system. Decoupled services like payments, inventory, and notifications are all listening. They receive the event and react simultaneously, executing tasks without waiting. Older pipes and filters setups process data strictly sequentially, passing information down an assembly line. This loose, decentralized connectivity prevents bottlenecks. If the analytics service gets overwhelmed, the payment service keeps running, keeping the distributed system resilient under unpredictable loads. The true test of these patterns comes when the system needs to change. Engineers face the challenge of updating and replacing core parts of a massive platform while millions of people are actively using it. To do this without crashing, engineers enforce the Liskov substitution principle. Any replacement component dropping into the system must perfectly respect the behavioral contracts and formats of the piece it replaces. Dynamic component models and application servers use this exact principle to selectively load, version, and unload specific components in real time. Data is temporarily routed around the target area. The live module is swapped out for a new version, and traffic resumes seamlessly. Swapping parts of a live environment is the engineering equivalent of replacing a jet engine while the plane is flying. Systems are built this way to continuously evolve without ever shutting down. At this scale, software architecture defines the communication, maintainability, and long-term survival of the platform. The platforms that dominate today did not succeed simply because they were coded quickly. They survived because they were specifically designed to grow. Components, event buses, strict layers, and dynamic modules all combine into an infrastructure that can heal, scale, and adapt.